So the initial activity of radioactive isotope is 120 becquerel, and the half-life is 20 minutes. For a sample of the same isotope with twice the mass, the values would be. So we've got a table of values where we need to say what the initial activity would be, and then what the half-life will be. Now, this is, do you know some facts? This is really, do you know some facts about radioactive half-life and radioactive isotopes? So the initial activity, now the activity, we do this a little bit more at A level, where the activity can be given by as being proportional to the number of radioactive nuclei present in the sample. So if you double the number of radioactives, if you double the mass of the sample, you double the number of radioactive nuclei in the sample, therefore you'll double the activity. So that's what's happening here. We double the mass, therefore the initial activity will be double. The half-life is entirely independent of how much of the isotope you've got. So the half-life of the isotope for this particular isotope is 20 minutes. It doesn't matter how many you've got of it, it's 20 minutes because the half-life is the time taken for the activity of the sample to halve, or it's the time taken for half of the radioactive nuclei that are present in the sample to decay. So all of these things mean that actually the half-life will be 20 minutes if you've got a billion of them, 100 billion, a trillion, whatever you like. The half-life is always 20 minutes. So that rules out these two. It means we're left with these three, and then we're looking for one where the initial activity is double because you've got twice as much, and that is B. Question 8. A fixed mass of gas is trapped in a syringe. The volume of the syringe is slowly reduced, compressing the gas without changing the temperature. The pressure exerted on the walls of the syringe changes because, so we had some gas. Okay, the temperature change is important because temperature change would mean that they'd be moving around faster. So you could increase the pressure by actually having the temperature increase. We're saying the pressure has changed rather than increases, but the reason why it's changed is the pressure is to do with how frequently and how hard particles in the gas are hitting the walls. Now, if you increase the temperature, they hit the walls harder and also more frequently because they travel around the container faster, therefore it takes less time between them hitting the walls. So if you keep the temperature the same but reduce the volume, then you've got the particles moving at the same speed, so they're covering the same distance, but because the walls are closer, they're going to hit the walls more frequently. So they hit the walls more frequently. It's exerting the same force when they hit the wall, but they're hitting them more frequently, so the pressure goes up. So let's have a look, see which of our answers best fits that understanding of physics. The gas becomes more dense is true, but it doesn't tell you why the pressure increases. Particles have more kinetic energy is not true. So I would say that's neutral, that's wrong. Particles collide with each other more often. That doesn't give you the pressure. It's particles colliding with the wall that gives you the pressure, although that is probably true. Particles hit the walls of the syringe. I'll leave that to be consistent. I'll leave those neutral. So the particles hit the walls of the syringe with more force. No, that's not true because that would be an increase in temperature. Particles hit the walls of the syringe more often or more frequently. I think I would prefer more frequently gives this idea of per unit time. So the answer is E. Light and sound can both be thought of as a wave. Which of these statements is not true? All waves can transfer energy. All waves can be reflected. All waves can be refracted. All waves can be diffracted. And what you can't have with a longitudinal wave is it can't be polarized. That's not really one, certainly the GCSE spec I teach, that we would necessarily go into a lot of detail. So that's the one. Transverse waves can be polarized, but longitudinal waves cannot. And sound is a longitudinal wave, so it can't be polarized. Last one. Aircraft has a mass, m. Thrust, that's a force. Aircraft needs to travel at this velocity. And the standing start time to become airborne is approximately how long? So a time. So we've got a mass and a force, which is going to lead us to an acceleration. And from a standing start, u equals 0. So I think I'm using v equals u plus at, which is a variation of that the acceleration is the change in speed over time. And I want the time on its own. So time on its own is v minus u over a. But I haven't calculated the A. The A I can calculate from these two. So A is F over M, rushing a little bit. 10 kilonewtons, so it's 10,000 over 4,000 is 2.5. And then the change is 35 seconds divided by 2.5. So check my 2.5 is correct. Yes, it is. Okay, then 35 divided by 2.5 gives me 14 seconds, which is D.